Good morning, everybody. Thanks for coming, and thanks for this opportunity to talk about our part of our research at the University of Barcelona. And I would like to thank publicly to organizers, because it has been a hard work to do this conference in hybrid format. So I'm very happy to be here personally. So as the chairman said before, the title of my presentation is The Pursuit of New Multifunctional Materials and the Encapsulation of Chromium as a Single Ion Magnet in a Spin Crossover Compound or Supramolecular Hosts. And I'm a synthetic chemist, and I will focus my presentation in this from synthetic point of view, because it's the most is the thing that I'm doing. So I would like to show you these complexes we prepare in order to be applied in quantum computing on spintronic fields, for example. So in general, we start our projects having an idea about the design and synthesis of our own organic ligands as a building blocks. So here I show you all the part of our ligands we synthesized so far, and I divided in three main families: the asymmetrical organic complexes, organic ligands, the symmetric ones, and also more extended organic ligands. And the idea here is preserve the presence of this the presence of these coordination pockets, the beta diketone, also the heteroatoms like nitrogen, because we want to favor the stabilization of iron 2 to study the spin crossover phenomenon. And also we would like also to include some spacers, and the idea to introduce these elements in the molecules is give more space between the coordination pockets, but also induce some chirality as well in our coordination complexes. And we want to introduce as well photoswitchable moieties in order to study our compounds from the optical point of view. So here is here we summarize on all the nice molecules we prepared so far, and this is like the inspiration corner for me, because here I show you all the complexes we synthesize, and these molecules have been sorry, it's not easy. Yeah, I show you here different complexes we synthesize, and maybe some of you remember the talk given by Professor Aromi last Saturday. And all these complexes are very important or very interesting in quantum computation, and also in as a photoswitchable molecules. So. Yes, so this story about the triple-stranded helicates, or these supramolecular complexes, started in 2014 as a part of a PhD thesis at the University of Barcelona. So we were able to isolate small anions like chloride or bromide using this small organic ligand. So the important future of this complexes is how the presence of these anions change the temperature where the spin transition takes place. As you can see here, the bromide decrease the temperature where the spin crossover is taking place in the complex. So when we change the organic ligand, in this case using a more long ligand like L2, we are able to encapsulate small, bigger molecules, as the case of chromium oxalate, which is encapsulated here. So the magnetic properties of this compound reveal we have a magnetic response coming from chromium at low temperature. And it's only because of the chromium, since the two iron of the helicates are in low spin state. So when we study in deep this complex, we realize that the chromium present slow relaxation of the magnetization for first time, which is not common in this ion. So also we did studies by using green light or the least effect, applying the least effect in this molecule, and we see how the 30% of the iron change their spins to low from low to high spin. So this possibility to externally control the slow relaxation of the magnetization of the encapsulated species. So until now, I'm showing you the published results, or the complexes that have been published so far. And now I would like to show you some new complexes, encapsulated metal oxalate, but also more extended molecules like this metallotecton. So why we are interested in the encapsulation of these metal oxalates, and it's because as Dana Freeman and collaborators published in this paper, these kind of molecules are interesting in quantum computing for many reasons. 3 of them are shown here. This metal oxalate has different spin states. Also, they present the coherence time, and the third important feature is they present also Rabi oscillations. So that is why we are interested in the encapsulation of these species. So, sorry. So when we did the synthesis using this extended ligand, the ligand L3, we successfully encapsulate the ruthenium oxalate inside this triple-stranded helicate showing spin transition. So the full characterization of this complex is right now in process, and because it is not easy to crystallize and to produce a good yield of this complex in a pure way. And also, when we use the ligand L2 and also the ligand L3, but I show you here only the ligand, the complex with ligand L2, we successfully encapsulate the iron 3 oxalate inside this cavity, and also the helicate presents spin transition. So the preliminary magnetic results for this compound show a gradual spin transition, and only 54% of iron change their spins, and but this is preliminary, and we are doing more studies about it. And the most one remarkable thing we observe in our compounds in general is they are stable in solution. So that is important to us as well. So here you can see the mass spectrum of the complex encapsulating iron oxalate, and the most important fragments are present. So they show how our compounds, the robustness of our compounds, so how robust they are. And we thought that the cavity of these helicoidal structures permit the encapsulation of more extended complexes, and it's the case of this metallotecton, the iron 3 anilate. And these moieties are very interesting from the coordination point of view, since they are able to, or they are very well known that they form a nice hydrogen bonded in supramolecular architectures. So when we did the reaction using the ligand L2, we successfully encapsulate this compound, and as you can see here, the anilate is coming out the cavity by these windows, or these empty spaces between the strands of the helicate. So the full characterization also is right now in progress. Here, this is a graphic summary of all the compounds, homoleptic helicates we synthesized so far. So we have this new family of metal oxalate encapsulated by iron, and also this complex encapsulated iron 3 anilate. So this is the family of homoleptic helicates we synthesized so far. And now we changed to another important thing we thought that was possible, and it is indeed, is the possibility to combine our ligands, short ligands and long ligands, in order to create heteroleptic helicates. And it's possible, and these reactions reveal also the strong template effect by this double charge anion, the hexafluorosiliciate. So it's able to form these heteroleptic complexes, encapsulating, at least at the moment, well, we have more, but at the moment I show you this complex, encapsulating hexafluorosiliciate. It doesn't matter the ratio you put in your one-pot reaction. It doesn't matter the ratio of the short ligand and long ligand you use, and also it doesn't matter the amount of iron or cobalt you put in the reaction. The result is always the same. You obtain this heteroleptic complex, and which is open huge possibilities for coordination. So here I show you the family of heteroleptic complexes we synthesize and we are producing now, and we have the complex of iron, nickel, and cobalt 2, and the complex of iron presents spin transition, and also we observe that the complex of cobalt presents relaxation of the magnetization. Of course, we need to improve these results, but at doing this experiment at higher frequencies, maybe, well, maybe not, yes. But yes, we see now an interesting behavior of this complex as well. So crystallographically, we observe also the presence of two different anions in this molecule. The hexafluorosiliciate is encapsulated inside this cavity, but the counteranions, the external counteranions, are different. They are hexafluorophosphates. So this shows also the stability of these complexes, the heteroleptic complexes, in solution as well, because we did the NMR, the fluor NMR studies, and we observe the presence of these two different anions crystallographically, because measuring the distances, but also in solution. So again, these compounds present a nice stability in solid state and in solution as well. So to conclude, or to summarize the important aspects we have in these complexes, I would like to remind that we have a family of homoleptic host system encapsulating chloride, bromide, all the family of metal oxalates, and perchlorate. I didn't show this because of the time, but these complexes show the influence of the encapsulated species on the temperature when the transition takes place. And also, for first time, we observe the slow relaxation of the magnetism of chromium-3, and the cavity of this helicoidal arrangement offer a versatile system for encapsulation of extended flat complexes or molecules beyond oxalate. So this open a huge possibilities for coordination and for interactions between these rings, and cooperativity as well. So this open a new for sure a new family of complexes in the future. Also, we have a great potential in these molecules in order to encapsulate good qubit candidates. So that is why we are very excited about these results. And the strong template effect show that this double charge anion is independent of the ratio of the compounds you put in your reaction, and also is independent of the crystallization method you use. And finally, this new heteroleptic host system has been produced, and this increased the potential of a combination of different organic ligands in order to modulate the cavity for coordination. Before finished, I would like to thanks to the group of GMMF at the University of Barcelona, especially Professor Guillem Aromí, Jordi Garcia, Paul Williams for all the advices and the state of art and all the scientific discussions. Mohana Daraushi, which in fact he started this project in 2014. It was part of this research was part of his PhD, and now Rosa Diego is finishing her PhD also as well. And also our collaborators, Olivier Rouault for scientific discussions and crystallography, Simon Titt in Berkeley, in the ALS in Berkeley for all the crystallographic studies, and very recently Dr. Valentin Novikov in INEOS Institute in Moscow. He was very interested in our compounds to study our compounds in solution. So now he's doing a nice collaboration with us in order to study this phenomena, the phenomenon of spin transition in solution, and all these projects for fun, and of course all of you for your kind attention.
Thank you very much, speaker.
Yeah, I think it's beautiful, especially if you just like can. I mean, you don't have to pay attention on the stoichiometry of the ligands, right? Yeah. I think that's really powerful. And once you have encapsulated it, can you actually get it out easily again? Have you tried any of these reactions?
Not yet, but this is one of the ideas I have in mind. For example, now we are trying to study the influence of the charge of the anion, because this anion is double charged.
Yes. Mm-hmm.
So we are trying to get the same compounds with hexaferrous phosphate, for example, which is geometrically is equivalent, and maybe the charge is very important. And also, I would like to do these reactions, putting two anions together, but after characterize the first one, dissolve this in solution and see what happens. Mm-hmm. If there is some interchange or not, or it's stable. We don't know, but yeah.
Okay, and then one last question maybe. So when you think about encapsulation of qubits, what would the qubit design need to be to actually get it in there? So what's your idea there?
Well, in general, from theoretical point of view, it's interesting because physicists all the time ask for this component, the possibility to encapsulate or to have some lanthanides around or something. So the possibility to encapsulate the metal oxalates, they are very qubit candidates, and also it's step by step, because lanthanides for sure is more complicated, and oxalate lanthanides are usually they are polymers, so it will be more complicated from a theoretical point of view. But it's because we know that physicists are very interested in this combination of futures.
Okay, thank you. It was beautiful. Thanks.
Okay.